The coupling alpha 1, alpha 2 and alpha 3 approximately satisfy the following equation. M is the mass scale, or momentum transfer scale, at which we want to calculate alpha I. Mu is a scale where the coupling is measured, and B1, B2, and B3 are calculated for the U1, SU2, and SU3 interactions. NF is the number of flavors with mass MF are smaller than M so that they enter the loop in figure. Alpha 1 is the coupling that is properly normalized for SU5. The negative contributions in the equation for B2 and B3 arise from fermion loops and the positive contributions from the gauge boson loops, gluons for SU3, Ws for SU2. Each gut will have some new particles that will occur in loops, so each gut will have slightly different Bi. Since the alpha I vary differently with mass scale, we can ask if at some mass they are equal. Define alpha 5 to be the value of the couplings when they come together at a mass M unif. Using two of these three equations, we have an equation which determines M unif. If we take mu equals MW, alpha 2 equals 130, and alpha 3 equals 0.11, M unif is approximately 10 to the 17th GeV. The precise number should not be taken very seriously since it depends exponentially on what we put in for alpha 2 and alpha 3, and is sensitive to the radiative corrections. The main point is that, if the couplings come together, it is at a very large mass scale or at a very short distance. Only there, about 10 to the minus 29th centimeter, could the forces of particle physics finally have the same strength. Graphically, we have approximately the situation in figure, since each 1 over alpha I is a linear function of natural log of M unif over mu. The slopes are determined by the Bi, that is, by the gauge fields and the particular group structure. Given the values of the alpha I measured at, say, Mz, and the slopes that are characteristic of the theory, we can calculate for any theory whether or not the forces unify. In some guts the couplings indeed meet at a point within the accuracy required by the measurements at Mz, for example in a supersymmetric SU5 gut. In the supersymmetric theory, the superpartners also enter the loops and change the coefficients somewhat. An interesting way to examine which theories give unification is to combine the running equations to give the following ratio. The left-hand side can be evaluated from data, and the right-hand side can be found from different theories. Let data gives the left-hand side at Mz equals 1.37 plus minus 0.07. In the standard model, the right-hand side equals 1.90, so the unification is approximate. When superpartners are included in the loops, and there are two Higgs doublets as is necessary in the supersymmetric extension, the right-hand side equals 1.4, which is consistent with the left-hand side given by the LEP data. Within experimental errors, the supersymmetric extension of the standard model fully unifies. This is one of the reasons people have been enthusiastic about nature being supersymmetric.